me well?
Yes.
Great. Yeah, my name is Eduardo Bañados, and it's my pleasure to have the opportunity to talk about some of the most distant supermassive black holes we know to date. So these are quasars that we can see even within the first billion years of the universe, or the epoch of reionization, when the universe changed from being neutral to ionized. So how many of these supermassive black holes we know to date at this early cosmic epoch of the universe? So let's try to put this into context on when was the first supermassive black hole at this particular time discovered. So this brings us back all the way back to 2000, so 20 years ago. So what I'm showing here is just redshift versus luminosity. And in the bottom, you have a histogram of all the quasars within the first billion years of the universe known. So the first one of this was discovered in 2000 with SDSS by Shoei Fan. And since then, we've made huge progress finding this very distant accreting supermassive black hole. So 10 years later, this census looked like this. So we knew about 60 of these objects. More surveys started to find these black holes. A few years later, we had 70 of these objects, so we started to now have enough to do some statistics. And in the last 5 years, there's been a huge progress on this. Like there are many
Eduardo, sorry to interrupt you. You
Yep.
you have the presenter mode, so if you can change this, it's better.
Oh, I'm sorry about that. Let me. Not sure if I can do that. Is that better?
Yes, perfect. Go
It's
ahead.
the same.
It's
Good.
working fine. Yeah.
Okay. So you were looking at the future. Right. So 2014, we had 70, and in the last 5 years, many teams have basically joined this effort, and the plot looks like this now. So we have more than 300 quasars within the first billion years of the universe. So this has been an increase of factor of 5 just in the last 5 years, and this is not the end of the story. So I know for a fact that there will be exciting new discoveries in 2021, so stay tuned. But now that we have this sample, right, and this sample is basically spread all over the sky, so we can just choose our favorite telescope, and we know where to point, and we know where to study these very distant supermassive black holes. And this allows multi-wavelength follow-up, because these are complex phenomena, right? So I always like to emphasize that when we find this object, we should take the opportunity to observe them with all wavelengths we can, right? So this is like the artist's impression we have for this quasar, this creating black hole, massive and living in a massive galaxy. And if you took your favorite X-ray telescope, for example, Chandra, and you go and take an image of this source, it looks like this. So this is actually, we can detect with Chandra even quasars all the way to redshift 7.5. And this gives us information about very close to the supermassive black hole, so the hot corona jets. But now, if we take now our optical near-infrared imager, and we take an image of the same object, it looks like this. So it's a very red source. And this is actually how we find these objects. We are looking for red sources in the sky. And now if we point with a spectrograph to this red source, it looks like this, right? So this is the typical quasar spectrum where we have a power law coming from the accretion disk. And on top of this, we have these very broad emission lines that we can use them to characterize the central supermassive black hole. And as you can see in the SED in this slide, if we go to longer wavelengths, then we have extra information. We start to see the hot dust in the mid-infrared. If we go all the way to the far infrared, then the cold dust from the host galaxies start to dominate. And if we go to radio wavelengths, then we have synchrotron emission. So all of this give us the complete picture of these complex systems. So now that we know that we have a sample of these very distant quasars, we know what they look like, and we know that we want to separate them in many wavelengths, I just want to focus the rest of the talk in some of the mysteries, puzzles, challenges that this population of supermassive black holes pose, and some of the this is just a selection. There are many more, but these are some of the main that keep me awake. So I'll talk about supermassive black growth, but since this conference has been mostly about this, I'm going to go very quickly through this topic, galaxies, and then radio jets at high redshift. So we've seen this plot a couple of times now. So this is just the black hole mass and redshift, and the points here are actual measurements of black hole masses of the most distant quasars. I'm highlighting here the most distant, the two most distant quasars that we currently know, and because these are the ones that set some of the most challenges for black hole formation theories. And the lines that you see there is like the growth of these black holes if they were accreting at the Eddington limit the entire time. So one of the key questions, as we saw in the previous session and also day one, is what are the black hole seeds that basically that can explain this population of supermassive black holes? So every time that higher and higher redshift, this problem gets even more complicated. And eventually what we want to hopefully see are directly the black hole seeds. And that will give us some information of this. And I'm very optimistic. So I think we're at the beginning of a new era of survey telescopes like Rubin, Euclid, Roman, and we will find high redshift AGNs. We know how to do that. But to be completely sure, because even if we don't detect them, right, so that would be very, very important for black hole formation theory. So we can rule out that they are accreting, for example, if we don't detect them at some of these lines, that maybe that means that they are accreting much faster than the Eddington limit. To be completely sure, it will be crucial to also have the new generation of X-ray telescopes like Athena, Axis, and Lynx. So I really hope they actually become a reality. And it's not only detecting them, right? So once you know they are there, of course, you want to measure the black hole mass to be completely sure what these objects are. And if you find a faint AGN that maybe is a progenitor of this massive 7.5 quasars, you will need the 30-meter telescopes to actually get a black hole mass. It would be very challenging, I think impossible with the current instrumentation. So we will have fun in a couple of years trying to get the black hole masses of these faint AGNs. So next topic, quasar host galaxies. So this is also something that I always like to emphasize, especially in a conference where it's not about galaxies, right? It's about supermassive black holes. But these quasars live in galaxies. We know that from low redshift quasars that this object lives in some of the most massive galaxies at every cosmic epoch. And in the low redshift universe, we have this tight relationship between the black hole mass and the bulge mass of the galaxy. We don't know if these high redshift quasar host galaxies have bulges. We have very little information about the stellar masses, but we do know that they live in very massive black holes. So we expect them to live in very massive galaxies. So for a long time now, the community have been trying to study the stellar light of the host galaxies of these quasars, and it's been extremely hard, basically impossible so far, even with HST. This is the example of what we try to do. So on the left panel, you have a HST image of a quasar, which is completely dominated from the accretion disk around the supermassive black hole. This can be thousands of times more luminous than the entire galaxy. But we know this is coming mostly from a region, very small region. So if we can model the PSF, the point spread function of the telescope, we can subtract that out and hope to see the standard emission from the underlying host galaxy. And as you can see, that's the right panel. And until now, this has been basically impossible. And we are hoping that James Webb will reveal the stellar light of this quasar host for the first time. But there's other options to study these quasar host galaxies. And now we actually have evidence that they are there. So as I mentioned before, if we go to the far infrared, then the accretion disk is not the dominant emission mechanism anymore. but the host galaxies of this, the cold dust of these objects, of the host galaxies. And we have powerful interferometers like NOEMA and ALMA that can actually detect, they can study specifically these wavelengths where we expect the host galaxies to be very bright. Before ALMA, we had some example, a handful of good examples with NOEMA or IRAM. So we knew that this could be done, but it was really difficult. But with ALMA, this has changed completely. So I'm gonna go through 3 of what I call the ALMA revolutions that has happened in the last few years. So one is the sensitivity of ALMA. So at the moment, we have detected more than 50 galaxies hosting these supermassive black holes above redshift 6. And ALMA is extremely powerful, right? In 8 to 30 minutes, you can detect a high signal to noise, some of the first massive galaxies that form in the universe, all the way to redshift 7.5. So these are just 2 examples of, so these objects are bright, 5 millijanskis, even the most distant quasars we know. The second revolution is that ALMA is providing resolution. So before we knew that there was a line there, but now we actually have a picture of some of the first massive galaxies in the universe. This is another example taking the redshift 7.54 quasar, where we see that the emission has a shape, right? So it's complex, it's elongated, it's not a quasi-stellar source. And we can also get the dynamics with ALMA. And for this particular object, we know that this is very likely to be a galaxy merger. So I find this remarkable that we can see, basically have a picture of a massive galaxy when the universe was only 5% of its current age. And we have a couple of examples of objects with this resolution, but ALMA can do even higher resolution than this. And the third revolution is that now we know that ALMA can detect this objects, especially in dust and C+ relatively easily. We can target different lines. And this is also another example of this particular quasar. And there are a handful of other quasars with even more lines than this, but we can start to do ISM physics when the universe was 700 million years old. Right, so we can, just by comparing these lines, and we can map them also at higher resolution, we can determine physical parameters like density, radiation fields on some of the first galaxies. So, and this is just starting. So I'm sure that in a couple of years we will have more examples and could do population studies of how different is the ISM in different quasar host galaxies. So the third topic, I think I still have time, is radio jet. So this is, I find this to be an interesting puzzle, right? So I think we all are familiar with these beautiful VLA images of radio jets that can reach hundreds of kiloparsecs. Right, so this can go outside the galaxy, reach the CGM, and they're just beautiful. But for some reason, we only know these extreme hundreds of kiloparsec jets up to redshift 4, and then we don't have many examples, or we don't have examples at all. And also jets, I think they are important for this conference because, as Alessandro showed before, and there are also a few other papers that they can also allow to the black holes to grow through super Eddington rates. So now if we go to the first billion years of the universe, and we ask, yeah, so how many radio jets, like extended radio emission we have? In this slide, you have all these sources. So there are only 3 where we have direct evidence of extended radio emission. These are all BLBA observations. And as you can see, they're small. So one of them is 200 parsec, they're 500 parsec, and the most extended one at the moment is almost 2 kiloparsecs. So that's one galactic scale. But this is it. So these are compact in comparison with the fabulous images I showed you before. So this has been known for a while in the community, and people have tried to explain well, why we don't see these 100 kiloparsec jets, and why are the ones that we see only small. And one possibility that has been put forward that I particularly like and I'm interested to test is that when you go to higher redshift, then the CMB is hotter. So the energy density gets higher, so it goes to 1 plus e to the 4. Um, so the CMB can quench the extended radio emission. So at some point, for the electrons, it might be easier to emit Barnes Compton scattering rather than synchrotron emission. And the prediction of this is that instead of seeing the extended radio jets at this redshift, you should see them as extended in X-rays. A couple of groups have tried to test this hypothesis, but it's hard. It's at the limit of what we can do with our current generation of X-ray telescopes. And in my group, we got 300 kiloseconds of Chandra to test this effect in this one quasar that has the most extended radio emission we know. So also one of the most powerful radio sources at this redshift. And so will be the second deepest X-ray observation for our quasar in the first billion years of the universe. We have exciting results, but I don't want to spoil them just now because we just submitted them, and I think I'll leave Tom Connor to share those results in the near future. Now that I'm talking about radio quasars, which I really like, also want to take the opportunity to mention that they can, in principle, provide critical information about the epoch of reionization. How? So this has been known for a long time. So it's something that's called the 21 centimeter forest. So it's similar to what we are more used to in the quasar community of Lyman alpha forest, right? But the Lyman alpha forest, you can only use up to redshift 6, and saturates, you don't get more information. But now if you have a bright background radio source, you can do similar experiment, but now you see the IEM in absorption in radio. So this is one of the main goals for the SKA, for example. So this is good, but the problem is that you need a very bright radio source in the background, and it's not clear if they exist. But if they exist, you can do this all the way to redshift 10. So recently, there are two important discoveries in this regard. So there are two radio quasars that are bright enough where this experiment will be feasible. So this is a quasar at redshift 5.8 and redshift 6.1. That there is also some of the ones that show jets. So perhaps this test could be even possible now. So we have a pilot program to see if it is feasible. But if it's not feasible, these sources are for sure good targets for the SKA. The problem is that they are a little bit at the low redshift end of reionization. So to take advantage of this, we really need similar sources but a much higher redshift. So the question is, do those sources exist? I'm an optimistic. So in this plot here, you see basically all the radio sources we know above redshift 5. And these two sources I showed before, I highlighted there with the ellipse. So they were discovered, one this year, one 2 years ago. So I think we will find, at the moment, the most distant radio source known is a redshift 6.2. And in my group, we are now trying to push this and find all the other sources that are a higher redshift and that they have strong radio emission. So recently we found one of those. This paper is already submitted. So it's a radio loud quasar at redshift 6.8. It's not as extreme as the ones I showed before, but it's a medium, like it's a typical radio loud quasar. And I think this is very positive, and I'm optimistic that we will find even more and perhaps even brighter. Kiara Matsukeli will talk about a little bit more in detail about this object in the next talk. But basically, with my team, we're following up all these sources with all the telescopes we can imagine, because we're really interested to push this frontier even further. So I think I'm almost the 20 minutes limit. So I'm gonna finish with this summary slide. Basically, these are the mysteries, puzzles, challenges I chose to share with you today: supermassive black hole growth, quasar host galaxies, radio jets. And I think we live in an interesting time I think we can do a lot of progress with all these puzzles with the current instrumentation, but really the next generation of facilities will probably solve many of these. So this is exciting. And thank you very much for your attention.